Good evening. My name is K. Bhagiraj. My roll number is 417. Today my topic is derive the transfer function and derive the transfer function and construct the block diagram of field control servometer and armature control DC servometer. And final and last one is AC servometer. And now explain the field control. And now explain the field controller DC servometer. There is a diagram in electric circuit is modeled as LF of S equal to EF of S by RF plus LF of S. Is his first equation. And now we see the diagram. Can't open. The electric circuit is modulated as LF of S equal to E of S by RF plus LF of S. This is the first equation, and another next equation is T of S equal to IF of S. This is the second equation, and third equation is JS square plus beta naught theta of S equal to T of S. This is third equation. Combining equations 1 and 2 and 3, we get theta of S by EF of S equal to KT by S of JS plus B naught RF plus LF of S, and KT by RF beta naught by S of J by B naught of S plus 1 LF by RF of S plus 1. Now we see the equation. Kf by RF beta naught S of J by beta naught of S plus 1 and LF by RF of S plus 1 LF by RF of S plus 1 and Km by S of Tm of S plus 1 Tf of S plus 1, where Km equal to Kt by RF beta naught equal to motor gain constant, tau m equal to J by beta naught equal to motor time constant, T off equal to LF by RF field time constant. The block diagram is shown below. First EF of S, and this is transferred to 1 by RF plus LF of S and by KT and 1 by JS square plus beta naught S theta of S. And field control DC servometers are economical where small size motors are required. For the field circuit, lower power servo amplifiers are sufficient and hence they are cheaper. The DC servometer and DC servometer is armature-controlled DC servometer, field control DC servometer, and second one is armature-controlled DC servometer. There is some requirements. RA equal to armature winding resistance, LA equal to armature winding inductance, IF equal to field current constant, EA equal to applied DC voltage, EV equal to back EMF produced by armature, IA equal to armature current depends of difference of EA, and J equal to moment of inertia of armature, B naught equal to frictional coefficient of armature, where theta equal to angular displacement. The torque produced by the motor is given by T equal to KT IA. This is equation 1. The back electromotive force is proportional to the speed of the motor, and hence E beta equal to K beta by, this is equation 2. And this equation 2 are a differential equation respecting the electrical system is given by RAIA plus less than a DIA by d theta plus EB EA. This is equation 3. Taking Laplace transforms of equation T of S equal to KT IA of S. EB of S equal to KB S theta of S. RA plus SLA IA of S plus EB of B equal to EA of S. Seventh equation is IA of S equal to EA of S minus KB S theta of S by RA plus SLA. The mathematical model of the mechanical system is given by J d square theta by dt square plus b naught d theta by dt equal to t. This is equation 8. Apply the Laplace transform of equation 8. Js square plus b naught s theta of s equal to t of s. T belongs to t of s. This is equation 9. Using equations 4 and 7, in equation 9 we get theta of s equal to kt, e of s minus kb s of theta of s, RA plus SLA, JS square plus beta naught s. This is equation 10. Solving for theta of s, we get theta of s equal to KT of s by s of RA plus SLA, JS plus B naught plus KT KB. This is equation 11. The block diagram representation of the armature controlled DC servo meter is developed in steps as shown below, representing equation 4, 6, 9 and 5 by block diagrams respectively. Combining these blocks respectively, we have the complete block diagram as shown below. And this is the final block diagram of this equation. Usually, inductance of the armature winding is small and hence neglected. The overall transfer function becomes T of s equal to theta of s by A of s equal to KT by RA by S of JS plus B naught plus KB KT by RA. This is equation 12, where KT by RA by S of JS plus B. JS plus B naught plus KT by RA. This overall the equation is KT by RA by S of JS plus B. This is the equation 13, where B equal to B naught plus KB KT by RA is the equivalent frictional coefficient. From equation 12, that the effect of a back EMF is increases the effective frictional coefficient. This providing increases damping. Equation 13 can be written in another useful from known as a time constant from given by T of s equal to Km by s of tau ms plus 1. Equation 14, where Km equal to Kt by Ra of s is the motor gain constant. Tau m equal to J by B is the motor time constant. Note, Kb and Kt are related to each other, and in MKS units, Kb equal to Kt into Kb is measured in radians. Note, Kb and Kt are related to each other, and in MKS units, Kb equal to Kt into Kb is measured in V by radians per seconds, and Kt is in N by Nma of A. Armature controlled DC servometer are used when where power requirements are large and the additional damping provided inherently by the back EMF is an added advantage. And finally transfer function is AC servometers. final one is AC servometers, and we can see the and I can explain the block diagram. Derivation is enough. Derivation is enough. First, we see the AC servometer definition. An AC servometer is essentially a two-phase induction motor with modified constructional features to suit servo applications. The systematic of a two-phase as a servometer is shown in below. It has two winding displacements by 90 degrees on the stator. One winding called as reference winding is supplied with a constant sinusoidal voltage. The second winding, called control winding, is supplied with a variable control voltage, which is displaced by plus or minus 90 degrees out of phase from the reference voltage. The major differences between the normal induction motor and an AC servo motor are: the rotor winding of an AC servo motor has a high resistance R compared to its inductive resistance X, so that its X by R ratio is very low. For a normal induction motor, K by X by R ratio is high, so that the maximum torque is obtained in normal operating region, which is around 5% of slip. The torque speed characteristics of a normal induction motor and an AC servo motor are shown below. The turkey speed characteristics of a normal induction motor is highly nonlinear and has a positive slope for some portion of the curve. This is not desirable of control applications, as the positive slope makes the systems unstable. The torque speed characteristic of an AC servometer is fairly linear and has a negative slope throughout. The rotor construction is usually circular cases drag for an AC servometer. The diameter is small compared to the length of the rotor, with reduces inertia of the moving parts. This has a good dynamic response. The supply to the two windings of AC servometer are not balanced as in the case of normal induction motor. The control voltage varies both in magnitude and phase with respect to the constant reference voltage applied to the reference winding. The direction of rotation of the motor depends on the phase plus or minus 90 degrees of the control voltage with respect to the reference voltage. For different RMS values of control voltage, the turkey speed characteristics are shown below. The turkey varies approximately linear with respect to speed and also control voltage. The turkey speed characteristics can be linearized at the operating point, and the transfer function of the motor can be obtained. The turkey, and now we see the derivation, of AC motor. The turkey is a function of speed theta and the voltage control voltage E. Thus Tm equal to F of theta comma E. This is equation 1. Expanding equation 1 in a Taylor series around the operating point, Tm equal to Tm naught, E equal to E naught, and theta equal to theta naught, and neglecting terms of order equal to and higher than 2, we have Tm equal to Tm naught plus tau Tm by tau in mod E equal to E naught, theta equal to theta naught, E minus E naught plus tau Tm by d theta, mod close E equal to E naught, theta equal to theta naught, and theta minus theta naught. This is equation 2. Note: since tau Tm by tau t is negative, beta will be positive. Equation 3 can be written as tau Tm equal to k del E minus b del theta. This is equation 5. Mechanical equation is given by J del theta plus B naught del theta equal to del Tm equal to K del E minus B del theta. This is equation 6. Applying Laplace transform of equation 6, we get a transfer function of an AC servometer as del theta of S by del E of S equal to K by Js square plus B naught plus B of S. This is equation 7. In a time constant, from we can write equation 7 as del theta of S by del E of S equal to Km by S of tau M of S plus 1. This is equation 8, where Km equal to K by B naught plus P equal motor gain constant, and tau M equal to J by beta naught plus beta equal to motor time constant. And this is enough, and thank you.